now. Just to check in, can everybody see and hear me okay?
Yeah.
Yeah, you're coming in clear.
Like a thumbs up in the, either a comment in the chat or like a thumbs up. Be good. My audio working the way that it should, because it's a little ambiguous on my side. Okay, thank you for just letting me know. We were discussing traveling waves at the end of our last lecture, and we were just about to start solving a problem. So I'm going to log in here on my tablet and bounce this over to OneNote so that we can solve this. Let me pull up our notes from last time. Okay, so we had just kind of started talking about developing a displacement function for a wave that's propagating in a known direction at a known amplitude, and then an angular frequency omega, and we introduced this wave number lowercase k, which is just the ratio of 2 pi radian and the wavelength of the wave that we are considering. So we're going to put that to work here with this snapshot graph. So we have knowledge of what this wave looks like at exactly one point in time, just t is equal to 0 seconds. It is traveling toward the left at a speed that we know. We're trying to write a displacement function that has units for everything, or units and values for everything, except for our two variables, position along the x-axis, and then the time, lowercase t. So let me switch over here. And I'm going to start sharing on this end. Okay, that's better. All right, so let's take a look at example 3 for chapter 16, the traveling waves chapter. Here is our snapshot graph that we were just discussing a moment ago. Oh, and for people talking about the echo, I think I had my mic on the tablet on as well when it didn't need to be, so that was making things a little hard to follow. Make sure that that's not going on here. Or I just jump right in. Okay, so we have a displacement versus position graph. The first thing that we can do is make a few measurements off of this graph so that we can determine the wavelength of this wave and the amplitude, capital A. So let's do the amplitude first. That's pretty simple to kind of indicate here on this graph. So just as a reminder, the amplitude is the separation between 0 on our displacement axis and either the most positive displacement value or the most negative. So here, I just chose this peak second from the right. This amplitude is 10 meters. Is equal to 10 meters. The wavelength I'll mark out in, I'll use this yellow color for this. So we're trying to measure the time from one peak to the next. And we have a couple of different ways that we can achieve that. I'm going to pay special attention to the fact that the wave at x is equal to 0 is neither at 0 meters nor at plus or minus 10 meters. So I'm looking for one complete wavelength. I could make my life a little easy and measure from one yellow dots to the next. And I see some comments about the video, or excuse me, the audio. Let me. Is this a little bit better? It looks like my mic was a little lower than needed to be. Okay, sorry about that. Okay, so let's keep going. Our wavelength is indicated by that yellow line, but of course, I can also indicate the wavelength like from here to here. I can choose these two peaks as long as they're adjacent to one another. So let's trace down here. We have 0.8 meters for the wavelength because I'm starting off of 0. So lambda is equal to 0.8 meters. I'm going to write this as a fraction for reasons that you'll see in a moment. So that's not 5 over 4, but 4 over 5 meters. And then the other quantities can be calculated from what is given to us in the snapshot graph and our wave speed. So let's start with the wavelength. If we know that that is 4/5 of 1 meter, we can calculate the wave number, which is this lowercase k. It's 2 pi radian over the wavelength. So 2 pi radian divided by 4/5 of 1 meter. We're going to end up with 10 pi over 4, or I can call this 5 pi over 2. And the units are just going to be radian per meter because I've got a meter in the denominator from the wavelength that we measured, and then this is just 2 pi radian. So when we multiply k by x, we're going to end up with something that is just a measure in radian. We'll see that coming up a little bit later. So now that we know k, we can use this to solve for omega. And I want to just kind of bring your attention back to one of the new formulas that we introduced at the very end of Monday morning's lecture. The wave number, k, is also equal to the, that's going to be omega divided by the wave speed. So we know what the wave speed is. We can determine what omega is. So let me write this not as k is equal to omega over v, but so that we're solving for omega. So omega is v times k. We know the speed of this wave. It is propagating at 50 meters per second toward the left. We just figured out what k is, so we can plug this in. So 50 meters per second. Lowercase v is representing a speed, not a velocity. We can account for the fact that this wave is traveling toward the left in a later step. So let's take 5 pi over 2 radian per meter. And here we see that our meters will cancel out and we'll just have radians and seconds left. Switch this so I can see. Okay, so I can see everything that you see. Okay, so we have 50 times 5 pi, that's going to give us 250 pi. Divide that by 2. This is 125 pi radian per second. And I'm leaving these in multiples of pi. It's not incorrect at all to approximate these as decimals. So we've got our K, we've got an omega. Probably what I should have done to start with is just written out this displacement function. So let me do that down here. D is going to be a function of both x and t. It is the amplitude times the sine of kx plus omega t plus our phase constant phi naught, where this plus sign comes from the fact that the wave is propagating toward the left. Okay, so our K value we've calculated, our omega value we've calculated, we measured A. The last thing to deal with is this phase constant phi naught. So what we need to do to determine phi naught is to take a look at the initial conditions. Use initial conditions. To find our phase constant. So let's go back up to this graph and take a look at it. We observed earlier that this snapshot graph at x is equal to 0, it neither starts on a peak or a trough, and it also is not starting at displacements equal to 0. So I want to pay attention to the value that this displacement graph has at x is equal to 0. So that is just x is equal to, excuse me, displacement's equal to 5 meters. So d as a function of x and t, and let me sneak a t is equal to 0 in here. That's just equal to 5 meters. Just reading right off of the y-axis. So let's use that down here. I'll say x is equal to 0, t is equal to 0. This is going to be equal to a times sine kx plus omega t plus phi naught, but I can plug some zeros in here. I know that this is going to be a 0, so that's going to cancel out that term that is the product of k and x. I also know that t is equal to 0, so I'm going to end up with 2 zeros plus phi naught. So it's going to turn into this, in other words. I'm going to fill in that 5 meters on the left side of the equation. I'll fill in the amplitude. We determined earlier that that was 10 meters. And then I have, let's put some parentheses around that so that we can keep these separate. I've got the sine of, and I'll use a square bracket here, 0 plus 0 plus phi naught. So I've got meters on each side. I'll cancel those out here. I have 5 is equal to 10 sine and then phi naught. So we can solve for phi naught just by taking the inverse sine of 5 over 10. So in other words, we're going to divide 10 from both sides. Let me just make this into a new step. So 5 over 10 is equal to sine phi naught. Therefore, phi naught is going to be the inverse sine of 1/2. Now, one point here, I'm not sure that I noted this. Measuring the angle, or we're kind of accounting for the fact that this is a periodic function. by measuring in radian. So make sure that your calculator is in radian mode whenever you're solving for or for a phi constant, or excuse me, for a phase constant, phi naught. So all I've got to do here, switch to radian, then calculate the inverse sine of 1/2. So what I end up with here is a decimal, but this is something that I can express in terms of pi, like I was doing before. So this is 0.5236, let's say. This is radian, but this quantity is equivalent to pi over 6. So now we've got the last unknown, or the last thing that we need to build our displacement function. So we've got a chat question: why is the sign changed to an inverse sign? Because we are solving for phi naught. So in order to undo the sign on each side, I'm essentially doing this. So the inverse sine of 5/10 is equal to the inverse sine of sine phi naught. So I'm just going to end up with the phi naught by itself on the left, and then my inverse sine of 5/10. Okay, you are welcome. Any other questions about how I got any of these quantities before we go back and build our displacement function? Okay, chime in either in the chat or on mic at any time. So let's make a little space here, and we're going to write out our displacement function. So d as a function of x and t is going to be capital A. We determined that that's 10 meters, and I'm going to use a lot of redundant parentheses just so that we can keep everything separate. So the units need to be here. 10 meters times the sine, and I'll use a square bracket for that entire expression inside the sine. K times x. And just as a reminder, we determined that K was 5 pi over 2 radian per meter. So let's put that in. 5 pi over 2 radian per meter. That's going to multiply by our variable x. Then I'm going to add, because this wave is propagating toward the left, omega times t. And I think no, we did calculate omega. Okay, so omega was 125 pi radian per second. So plus 125 times pi radian per second times t. And then our last step is to add this phase constant. And we determined that that value is equivalent to pi over 6 radian. And again, just to kind of highlight, the units of everything inside of the square bracket is going to basically drop down to just radian, because I have a distance in meters, whatever that, or really not a distance, but a position in meters, that when multiplied by 5 pi over 2 radian per meter is just going to leave me with radian. And if I measure my time in seconds, then multiplying 125 pi radian per second times some time in second is just going to leave me with radian. So I have radian plus radian plus radian inside of the square brackets. And we are finished with this example question. So we've got units and values for everything except for the x and the t, our two variables. All right, let me peek at my laptop here. This is the last slide in part 1 of the traveling waves chapter. So while I am opening up the second part of this chapter, Is there anything about this question that you need to see or hear one more time? All right, seems like we are good here. So let me stop sharing so that now I can share on this end. And let me see. Share PowerPoint. Okay, and we're ready to take a crack at the second half of this chapter. So just as a like a quick refresher, we are still talking just about mechanical waves, so the type that can propagate through a string, like the I think we talked about like a jump rope attached to a doorknob or something like that. That would be an example of a transverse wave, because I would have to move my hand up and down in order to get a wave that propagates from side to side. And then a longitudinal wave is the type that I could generate on a slinky or a spring. It's also the type of wave that is propagating through the air in my room so that my mic can pick it up and transmit it to you wherever you are. So instead of a disturbance that is perpendicular to the direction of the propagation, a longitudinal wave is created when a disturbance is oriented parallel to the direction that the wave is actually propagating. Now we're going to kind of take a step back and go back to a semester one concept. And I mentioned very briefly at the beginning of Monday morning's lecture that we are developing a new wave model, but we have had some experience developing models that led up to this. The very first day of semester one, we started with the particle model. And now we realize that while the wave that we are through this string, each point on the string itself can be treated as a particle. So that means that our kinematic equations that we encountered back when we were discussing simple harmonic oscillation in semester one, and our logic related to Newton's laws of motion, they're both relevant to this view or this analysis of this wave on a string. So to say that in a less clunky way, while the string itself is not moving left or right, there are segments on the string that are moving or that are constantly in the process of wiggling up and down. So we can write kinematic equations for each of these little particles that represent a single segment or a small section of string. So since this is our transverse wave and it's propagating horizontally, the displacement has got to be oriented along the y-axis. So our kinematic equation, just like our displacement function that we just finished constructing, is going to be a function of both x and t. But we are trying to actually determine like a position along the vertical axis. So we are swapping out capital D with just a generic y. So we have, in this image here, we know that this wave is propagating toward the right. So we know that there's going to be a negative in between our kx and omega t terms in each case. Our logic from our discussion of simple harmonic oscillation in semester one should kind of remind you that if we have a kinematic or a position function for a simple harmonic oscillator, if we take successive derivatives of that, we can turn it into first a velocity function and then an acceleration function. So dy dt, the first derivative of that y, that vertical position function, is going to yield a negative omega a cosine, and then everything inside of the parentheses is going to stay the same. The omega that comes out front is a result of the fact that we're taking this derivative with respect to time, and time is multiplied by omega. And then we have a negative cosine that is the derivative of sine. Take one more derivative and we're going to end up with an acceleration function. So negative omega squared times a sine, everything inside the parentheses stays the same, where our additional omega comes from the fact that the t in our velocity function is also multiplied by an omega, and the derivative of cosine is sine. So the negative sign is not canceled out when we're going from the vertical, the velocity function to the acceleration function. So imagine that we wanted to produce a, not really a motion diagram, but we're kind of thinking about this section of, well, this length of rope that's oriented along the x-axis. We're kind of thinking about this like a snapshot graph, where at this one point in time, each one of the particles that makes up a segment of the rope is experiencing an acceleration. The velocity of the different sections of the rope is going to vary based on whether the rope is already at its maximum positive displacement or its maximum negative displacement, or if it is working its way between those two bookends. So in other words, if you take a look at the particles that match up with the peaks and troughs of this little segment of wave, there's no velocity vector attached to it, because this section or these sections of the string are already moving up as far as they're going to along the y-axis, in the positive direction, and this particle has moved down as far as it's going to. So it's in the process, or that section of rope is in the process of changing its direction. Just like if you were to take a ball and toss it up in the air, when it reaches its highest point, it's instantaneously going to be at rest because it's in the process of going up and slowing down and turning, or it's in the process of going from moving up and slowing down to moving down and speeding up. That also suggests that we should be able to find a point at the midpoint. So any one of these positions that is lined up with the x-axis is going to be moving with its largest possible speed, either straight up or straight down. And then all of the points in between those extremes are just going to kind of scale appropriately. So we start off with this leftmost velocity vector. It's got the largest magnitude, it's oriented down. Next, we have a downward pointing velocity vector that is a little bit smaller in magnitude, a bit smaller until we zero out up here at the top. Then the behavior kind of inverts, where now our velocity vectors are increasing in magnitude instead of decreasing, and they're pointed up as opposed to pointing down. One thing to keep in mind, though, that this first derivative, which is the velocity function, dy dt, this is not the same as the speed of the wave on a string. We can calculate the speed of the wave on this particular string by either taking a snapshot of it and measuring a wavelength and comparing that to maybe a known frequency, and we can take the product of those two, or we can achieve this by having some knowledge about the properties of the medium. So the linear density of the string and its tension. Combining those can also give us the speed of the wave on the string. But this velocity in the y direction is not the same as the wave speed that is oriented in the x direction. So if we were to take a look at just one section of string, and we're going to choose a section, just to roll back a moment, a section that is at one of these peaks. So this section of string is as far away from the horizontal axis as it's going to be capable of getting, and it's going to be on the positive side as opposed to the negative side. We know that if we are applying the particle model to this one section of string, we can come up with some way to explain the mass of that segment and then apply Newton's second law to it. And that's exactly what we're doing in this first statement here. So there are no horizontal forces acting on this section of the rope, purely vertical ones. So the net force in the vertical direction is going to be the mass of that section or that segment of string times the acceleration in the y direction, where the acceleration in the y direction is literally just this acceleration function from the bottom of the previous slide. Now, unless we were to actually cut the string and then mass out a certain length delta x, we have to have some other way to come up with a way to explain the mass of that one segment. And if you think back to our definition of linear density, the mass per unit length if we know the linear density for either this specific string or just this type of string, then the amount of mass contained within that segment is going to be the linear density times the width of that section, or that segment. So delta x times mu is going to give us a mass in kilograms. So there's our force expression. We can play around with this a little bit more because we, let me go back. Oh, hold on. No, we can stick with our wave number. That's what's being indicated here with the green text. So if mu times delta x is equal to the mass, and we just determined from the previous slide that our acceleration function is going to be negative omega squared times a times sine kx, blah, 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 blah. I can cut out the blah, 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 blah part because I know it's going to show up on both sides of my expression. So I'm just going to keep the negative omega squared and the a, and then the sign of everything inside those parentheses is going to cancel. So negative omega squared, I can write that in terms of the wave speed and the wave number because I know that omega is just equal to v times k. And next, I can take into account, or I can really apply not apply, but I can always determine or express the net force acting on some object two ways. First, just by taking the mass of that object and multiplying it by the acceleration. But the other method is to add up all of the forces that are acting on that object. And since we're just talking about the y direction, if the tension in the string is going to be oriented kind of down into the left on the left side of the string and then down into the right on the right end, I can measure an angle between this tension vector and the horizontal, and then use that to decompose that red vector into purple components. So I've got two downward tension components, or two tension components that point toward the negative y axis. So I've got TS times this is going to be the sine of theta on the left, and then TS times the sine of theta on the right. So 2 TS sine theta. Now the purple ink here is indicating we're using the small angle approximation. And in general, if you are dealing with an angle that is fewer than about 10 degrees, the sine of that angle is not going to be very different than the tangent of that angle. So I'm going to replace that sine theta with a tangent theta. So F net can be written as 2 times the string tension times the tangent of theta. The tangent of theta is just going to be the opposite over the adjacent. So I can write tan theta as this ratio. So k squared times a delta x over 2 with a negative sign because both of these tension vectors point down. If we put all of that together and solve for v, the one that shows up in the green, we are going to end up with the wave speed expression that I just kind of introduced and kind of asked you to believe it the first time that we encountered it on Monday. But here's justification for that. This is why that expression works, and it's where this expression comes from. Just an application, or really a combination of applying dynamics to the segment of string and then combining it with the kinematics from the previous slide. That's where I got acceleration is equal to negative omega squared a times this sine blah, blah, blah. Pop the chat open because I realized I did not open that there. It looks like we're still good there. Chime in with any questions at any time if you have them. What we are getting ready to do here is a kind of twofold. Two things are going on. First, we are going to learn to deal with waves that are propagating in more than one dimension. So just to backtrack to this image, back to that image, really this one here, we were looking at a wave on a string where the direction that the wave was propagating was really constrained by the string itself. So in other words, if you imagine setting up a rope and like attaching one end to a doorknob and then wiggling the other side of the rope vertically, There is nothing that you could do to make the wave that you're producing propagate any direction other than away from your hand and toward the opposite end of the rope. And again, we are not yet talking about what happens when that wave reaches the boundary, which would be the doorknob for me, and reflects back on itself. That's going to be a topic for chapter 17. So for now, we're just kind of paying attention to what the wave is doing when it's propagating in just one direction and not interacting with itself. If we are instead talking about a different type of, or not necessarily a different type of wave, it can still be transverse, but a medium that is not confined to one dimension, then the wave that we can generate can be capable of moving in either 2 or 3 dimensions. We have a 2-dimensional example here. Imagine that you're standing by a calm pond, you take a rock and you throw it into the pond, and then you pay attention to, let's say maybe there's a leaf that's on the surface of the water. So that leaf is going to bob up and down as a result of the wave that you generated by throwing a rock into the pond. And that wave is going to be constrained to the surface of the pond. So that's a plane, that's 2-dimensional. What we see here on the left-hand side is a diagram that kind of acknowledges that the wave that you are producing by throwing a rock into a pond is going to travel radially outward from wherever the rock actually touched the surface of the liquid. But there's still going to be a wavelength, a frequency, and a wave speed that we can associate with that event, just like the wave on a string. Now, this little kind of transverse wave that we see at about like the 4 o'clock position in this diagram, this is what you can imagine seeing, or what you would be able to see if you could toss a rock into the pond and then take a vertical slice of the pond so that you can just see when the water is at its maximum vertical position, when it's at its minimum vertical position, and when it's at equilibrium, or really anywhere in between those 2 extremes. So what you would see is that the circles, the concentric circles that look like they're spreading out from the point on the surface where the rock actually entered the pond, they're separated by 1 lambda. So that also means that this outermost circle, or this outermost wavefront, was the earliest one that was generated, and new ones are being generated right here at the middle. So they are kind of acting as the source. Now, if you imagine that instead of you standing near the bank of this, by like the bank of this pond, I suppose, and throwing a rock into it, imagine that your lab partner is in a helicopter, let's say, and they drop a rock into the middle of the pond. And it's your job just to wait until these wavefronts propagate out towards you. You're going to notice 2 things. One, the wave amplitude, or like the height, is going to get smaller and smaller the further away from the source the wavefront propagates. But also you would notice that once you got far enough away from the actual location where the rock entered the pond, you would kind of start to lose sense of the curvature of those wavefronts. So in other words, if you can get far enough away from the source of a wave, even though it's 2-dimensional, these wavefronts are just going to look like parallel straight lines that are propagating in just one direction, because you can only be standing at one location on the bank of the pond. You can't be in all locations at the same time. So if you're just evaluating the wave that's propagating towards you, it does look like it's traveling in just one direction. Now, the diagram on the left is exactly the same as what we saw in the previous slide, but now we're going to think about it in terms of a 3-dimensional wave. So this is something that is maybe a little difficult to visualize if we're trying to think about a light wave. It's not at all difficult to visualize if we think about how light just works in general. So I'm sitting in front of a lamp. The light that's being generated by that lamp is traveling outward in all directions. So that means that if I were to walk around my room, I wouldn't be able to find a dark spot where the light just wasn't capable of reaching. it's traveling outward in all three dimensions. Sound waves behave the same way. So if you were in the same room with me, you wouldn't have to be at exactly the same vertical level to hear my voice or exactly the same horizontal position. That sound wave is going to propagate outward in all directions. So instead of thinking about these circles that we see on the left-hand side as being circular wave fronts that are on the surface of a plane, like the pond example from the previous slide, imagine that what we're seeing is really just a cross-section of a sphere, or like a shell, really, that's expanding outward. Those adjacent shells, or those adjacent surfaces, are still going to be separated by, or from their nearest neighbor by exactly 1 lambda. They are still going to be some mixture of large displacement, or like maximum displacements, zero displacement, and then the minimum or the negative displacement, and then all points in between. But now we can imagine taking a slice of this 3-dimensional wave and recognizing that these planes represent segments of that same imaginary shell that I asked you to imagine spreading outward. So instead of, on the previous slide, like we see here, the wave fronts just being straight lines that are 1-dimensional, for a 3-dimensional wave, the wave fronts are planes, or 2-dimensional, and they have something in common with one another. The phase that is, or I should say that any wave that intersects one of these planes that represents a line or a surface of constant phase, they're all going to intersect with the peaks of these 3 blue waves. So in other words, let's think back to the way that we defined a wavefront back on the previous slide. We said that the section of the, or like the ring that looks like it was expanding outward on the surface of the pond, represented a section or an area of water that had a higher than average vertical position. So the midpoint between those 2 wavefronts should be a location where the water had a lower than average, or its lowest displacement. We can see that that's also true here. If we look at the midpoint between 2 adjacent surfaces of constant phase, we're going to find a trough as opposed to a peak. So these 2 diagrams, this one that's on the left-hand side and the one that we saw on the previous slide, they're identical, but we can think about them as being just something that's happening on a 2-dimensional surface here in the first case, and then a cross section of a 3-dimensional shell for the next case. So what we want to do is really come up with some way to adapt our displacement function so that it will apply to 2- and 3-dimensional waves in addition to 1-dimensional waves. And we want to kind of dig a little bit deeper into what phase means in this context. And I know that we talked about phase in semester 1 when we were going over simple harmonic oscillation. And the phase constant here is kind of our way to account for the fact that, I don't want to jump back over to the other, well, hopefully it's not too distracting. Let me jump back over to the last slide of the previous part. So this problem that we worked on. If this is a snapshot of a wave that's got the properties that we were given and the ones that we determined, this snapshot just pertains to one moment in time. So imagine that we were in lab. I had a big rope that was stretched out across the lab, and I asked each one of you to take a picture of it on your phone. I wouldn't be able to ensure that every single one of you takes the picture at exactly the same moment. So you might have pictures that look a little bit different, but they all describe exactly the same wave. If we wanted some way to confirm or to compare all of our individual snapshots to one another, what we would want to do is basically develop some way to indicate what the wave looks like, or not really what the wave looks like, but what the string looks like at x is equal to 0 and t is equal to 0. So to jump back over here, the stuff that is inside of this sine function is the phase. And this is phi without a subscript because we are, I guess, describing the entire phase or complete phase. We're not trying to scale it back to some common factor.
So I kind of glossed over this stuff up here at the front. This statement, or this stuff at the top, the statement at the top is just our way of changing variables, so that instead of confining ourselves to a wave that is propagating in the horizontal direction and that has a displacement that's in the vertical direction, we can go to radial coordinates, so that d can be a function of r and t, and the amplitude is also going to change with radial position. Think back to when I asked you to imagine your lab partner dropping a rock into a pond while you just observe it from the edge. I mentioned that the amplitude, or like the height of the displacement that, or the wave that you would see from the edge of the pond, would get smaller and smaller the wider or the further the wavefront stretched out. That's all that's being acknowledged here. A is a function of r, so that when r gets very large, a drops down. This is different than what we saw for the wave on the string, because we were evaluating a case where there are no damping forces. So the amplitude of every peak, or I should say the maximum displacement of every peak that you would measure, would be the same. It wouldn't die off or drop down. Or drop down or die off is probably what I wanted to say there. So since the rock and pond example, since dropping a rock into the pond would never produce a wave that just moved inward, we wouldn't have to worry about determining whether we needed a plus or a minus here in between our kr and our omega t. It would always be a minus, because the wave is always propagating outward, not inward. So if we know that this quantity inside of the sine function, this kr minus omega t plus phi naught, is always going to be the same value, we can replace all of that just with a phi with no subscript, so that we've gone from our displacement function for a wave that's propagating in the x direction to one that's propagating radially outward, and we can set that equal to the amplitude times the sine of the phase, not the phase constant. So let's take a look at this would be another snapshot graph of a wave that has some unknown amplitude, a wavelength that we can at least label here in the diagram, but we don't have any numbers to attach to it yet. So purposefully, we're looking at 2 points that are somewhere in between the maximum displacement, the minimum displacement, and 0. So in other words, I'm not choosing peaks, I'm not choosing troughs, and I'm not choosing these intersections where x is equal, or where the displacement's equal to 0. I'm specifically going for points that are somewhere in between. So if these points are somewhere in between, and as I can see here, the separation between these 2 points, x2 and x1, is larger than the wavelength lambda, I can come up with some way to express the, I guess, the linear separation between position x1 and x2, and then turn that into a phase difference. So phase difference is delta phi, phase constant is phi dot, or phi naught, or phi sub 0, and the phase is just phi on its own. So position x1 has some phase that is k omega, or kx minus omega t plus phi, but with an x sub 1, so that we know we're talking about position x1, and then this phase constant, because our goal here is still to compare something that's common about both the phase at position x1 and x2, and this phase constant is developed, or it plays exactly that role. So we want a phi naught here. It wouldn't be appropriate to say that phi 1 is equal to all this stuff plus phi 1 again. So our phi 1 and our phi naught are different, in other words. We'll do exactly the same thing for x2. And since we're looking at just one wave that's propagating in one direction, I'm going to have negative signs or minus signs in both of these expressions. So if my goal is to calculate the phase difference, delta phi, I can just take these two expressions and subtract one from the other. And what we end up with after we do some algebra is 2 pi delta x over lambda. And this should look familiar, because this term showed up when we were developing our displacement function at the end of Monday morning's lecture. We were taking a look at a function that we knew was periodic, so we knew that there was going to be some repetition in there, and we ended up with a 2 pi times x over lambda that we were able to express in terms of a wave number. 2 pi over lambda is k, and then delta x is delta x, the separation between x2 and x1. So the phase difference between any 2 points on this wave can be calculated exactly the same way. If I were to find some point x3 somewhere on this string, I could find the phase difference between x2 and x3, or x1 and x3. Because this is exactly the same wave, I know for sure that k, omega, and phi naught are going to be the same for any 2 locations that I choose. Okay, so we're still kind of talking about 2 and or 3 dimensional waves. And when we were talking about 3-dimensional waves a few moments ago, I mentioned that both light and sound are examples of 3-dimensional waves. So we're going to take a little detour, I suppose, to talk about how to deal with this specific type of 3-dimensional wave, one that propagates through the air in a room. Or maybe if you are underwater, let's say you're in a swimming pool and somebody drops a rock so that it hits the bottom of the pool. You'll be able to hear that. It wouldn't sound exactly the same as it sounds if someone were to drop a rock on concrete and you were standing in air. But my point is that sound is still traveling through that water. So what we know about how sound travels through air can be related to how sound travels through a liquid or even through a solid. To relate this to air, this is most similar to this week's lab experiment where we're creating a sound wave, graphing it with Logger Pro, and then making some measurements so that we can determine what the period of that sound is, or what the wavelength of that sound is. Imagine that instead of a tuning fork, you have a loudspeaker that's going to just move backward and forward, or like the speaker cone, really, that's going to move back and forth. And as a result of that motion, the particles, or like the air molecules that are in this imaginary space, they're going to either end up pushed closer than they were before the sound was generated, or spread further than they were when the sound was generated. It's kind of like the coils of the spring that we talked about in Monday morning's lecture, where some sections are closer than average, some of them are spread wider apart than average, and then there are the sections of the slinky that are either waiting for the pulse to go through it, or the pulse has gone through it and they've had time to kind of go back to their equilibrium. So it's easy to kind of visualize and assign a name to what happens when you take a bunch of molecules and squish them together. That would be a compression. But the opposite of a compression, or a compression, is a rarefaction. And this is something that you can kind of observe, or it's similar to what you observe if, let's say you open a window in your bedroom and you've got light curtains, so that when you close the door and then open it again, you can kind of see those curtains kind of get sucked towards you or sucked toward the doorway. That is a result of the fact that you are initiating a pressure change when you open the door after it had been earlier had been closed. You're also doing something similar when you close the door in the first place, but opening the door is going to cause the air particles that are in the room to spread out a little bit further. And that's what happens in between the compressions that are being produced by the speaker cone that's moving back and forth. So I've got areas where the density is higher than average, areas where the density is lower than average, and they're separated by one wavelength, just as we saw with the spring that's got a longitudinal wave propagating through it. And we saw this a bit earlier when we were talking about our 2- and 3-dimensional waves. So the distance between adjacent wavefronts is equal to lambda in that case, or those cases, I should say. It's also equal to lambda in this case. So if we are specifically discussing the speed of sound in air, there is one way that we can change the value or the speed at which sound travels through that air without changing like the mixture of gases. So whenever, if you've ever done this yourself or just seen somebody take a lung full of helium and their voice sounds different, the fact that their lungs are now holding a mixture of ordinary air and the helium, that change in composition will affect the speed, excuse me, it will affect the speed of a sound wave that that person can generate. However, if you're not mixing gases and you just have one type of gas whose temperature you can change, then the hotter that gas is, the faster a sound wave will travel through it. The cooler the gas, the lower the sound wave will be. And we can use this expression here to calculate the speed of sound in air for a given temperature. So this is the speed of sound as a function of temperature in Celsius degrees. This is 331 meters per second, plus this product here, where inside the large parentheses, we have 0.600 meters per second per Celsius degree. So if we plug in a temperature in Celsius, we're going to have some term that's in meters per second added to meters per second. And if you are given a question that tells you that the air in the room or the air in the whatever scenario you're trying to evaluate, if you know that it's happening at room temperature, then you know that the speed of sound is going to be 343 meters per second. That's achieved just by plugging a 20 degrees Celsius into this expression and then solving for it. But if the speed of sound, or excuse me, if the temperature is maybe more like 25 degrees Celsius, you're going to get closer to like maybe 345, 346, 347. So in an exam scenario or like a lab scenario and homework as well, if you're not given a temperature, it's safe to assume that the scenario is happening at room temperature. But if you are given a temperature, here's how you can determine what the exact speed of sound is. Now, we know that, well, let me put it this way. If you had lab earlier in the week, you got to see an example of a wave that's moving through just one medium. So one constant medium. Imagine a string that is not fraying, it's not connected to anything else. If you were to change the tension in that string, you can change the wave speed because the linear density is staying constant, but T sub s is changing. If you were to change the rate at which you are wiggling one side of the string, what you would ultimately change is what the wave looks like. So like the shape of the wave, whether the peaks are spread out or whether they're compressed. You wouldn't be capable of changing the speed of the wave unless you changed either the string tension or the linear density. So what this is telling us is that the same air, the same 20 degrees Celsius air can give rise to waves that have different frequencies, that have very different wavelengths, but they're all traveling at the same speed. So we're going to refer from time to time to the range of human hearing for like a healthy human ear. The lowest frequency that you can pick up or you can detect is around 20 hertz, and then about 20,000 hertz is the highest frequency on the upper end that a healthy human ear can detect. And down here below, there's just a calculation that shows you just how different these wavelengths are. Both of the waves are traveling through the same air at the same temperature, so they have the same speed. But the frequencies being different means that the wavelengths are going to be different. So the larger frequency is going to be paired with the smaller of the two wavelengths, and the lower frequency is going to be paired with the larger of the two wavelengths. Now, another example of a three-dimensional wave is a light wave. There is more to this discussion or more to this topic that we're going to encounter not in the next chapter, but the two chapters that follow that one. For the time being, we're just going to think about a light gray that is propagating through space. We're not yet going to think about how that wave can interfere with itself or how that wave is going to interfere with matter. We're going to leave that for a topic or discussion next week. Maybe the week after, actually. So if a light wave is propagating through a vacuum, we know how quickly it can move. This is something that we can measure experimentally, and the speed of light in a vacuum is about 3 × 10⁸ meters per second. That's about 300,000 kilometers per second. That light wave is something that's, well, let me state it this way. We are pretty familiar with the different ranges or the different areas of the electromagnetic spectrum. It is really easy to overlook the fact that, like, for example, AM and FM radio are examples of the same type of light that we can interact with coming from our lamps, that we can see when we go outside. In other words, the type of light that human eyes can detect is just one small region of a much larger spectrum. And that is kind of laid out down here, where we have the higher frequencies on the right-hand side. And again, if we're assuming that all of this light is traveling through the same media, let's say a vacuum, then as the frequency goes up, we know for sure that the wavelength is going to go down. So the frequency increases toward the right, wavelength decreases toward the right, or I can say that wavelength increases toward the left. So I have wavelengths, or like approximate wavelengths in meters, and then approximate frequencies in hertz. If I take any one of these examples and multiply them together, top and bottom, I'm going to end up with the speed of light. It's easiest to see here if we look at the FM radio TV range, because those wavelengths are on the order of a meter as opposed to hundreds of a meter or hundredths of a meter. So 3 meters times 10⁸ hertz gives me 3 × 10⁸ meters per second, where remember hertz can be written as 1/second. It's super tempting to see radio on the left side, or like the low frequency end of the spectrum, and only think about the way that most of us experience radios when we're in our car most frequently, right? You might turn on music or turn on whatever it is you're listening to, and think about the trip between your speaker, which is generating a sound wave that propagates through the air that's in your car, your ear detects it. But when we're talking about light or an electromagnetic wave, don't think about what you're hearing from your car speaker. Think about what had to have been transmitted from the radio station to the receiver that's in your car radio. That is a form of light, very low frequency light. So in other words, light that has a wavelength that's way too big for human eyes to interact with, but it still propagates through space at exactly the same speed as the sunlight that we observe coming from our sun, or the light that might be coming from a lamp in the room that we're in. So in reality, C, or the speed of light, is a bit less when it's traveling through atmosphere as opposed to traveling through a vacuum, but the difference is small enough to be ignored if we're just talking about how this impacts wavelength and frequency. We can deal with it if we are trying to concern ourselves with the concept of the index of refraction, which I think is coming up on the next slide. So put a pin on that, or in that. We're going to get to it shortly. So from low frequency to high frequency, we have forms of radio. They're split up into AM and FM for this example. And then TV here, this is kind of an acknowledgement of the way that old over-the-air TV worked. Next up, when the frequency is a bit higher, but the wavelength is a little bit shorter, we run into microwaves. Then infrared. So this is the type of light that human eyes can't see, but we can easily feel on our skin as heat. It's kind of why, well, one of the reasons why, if you were to go outside in the summer and let the sun shine on you, you would feel warmth because of that infrared, I guess, infrared light that's interacting with the receptors in your skin. Then we have the visible spectrum that encompasses all of the colors that we are familiar with, the ones that learned since we were little kids. Then on the opposite side of that, wavelengths that are a little too short for human eyes to pick up, that's ultraviolet. Then we go into X-rays. And this diagram stops short of including gamma rays. I'm not sure why, but most electromagnetic spectrum diagrams that you'll run into will have a dedicated section for gamma rays, which are higher energy or higher frequency than X-rays. So we would expect a frequency even larger than 10 to the 18 and a wavelength even shorter than 3 times 10 to the negative 10. One thing to kind of keep in mind here, or to remind ourselves of, the visible spectrum is just the small section of the larger spectrum, but it's bounded by about 700 nanometers on the red edge, or a wavelength of about 700 nanometers on the red edge, about 400 nanometers on the violet edge. We're going to run into that idea again in lab number 3. Okay, let me peek in the chat. Looks like we're still okay here. Does anyone have a question that they need to ask on mic while we're paused for a moment? And jump in at any time if you do have questions. So on the previous slide, I mentioned that in reality, light travels a little bit slower when it's moving through atmosphere than it would if it was just moving across the vacuum of space. This is something that's true for light traveling through any transparent or at least semi-transparent material. And we can kind of measure or communicate how severely a material slows down light by introducing this concept of the index of refraction. So this is lowercase n. It's a unitless quantity because it's just the ratio of 2 speeds. It's the speed of light, c, divided by the speed of light in that specific material. So if we were applying this to Earth's atmosphere, the speed of light in Earth's atmosphere is going to be a little bit less than 3 times 10 to the 8 meters per second. So that would give us an index of refraction that is only a slight bit larger than 1. I think the value that we'll see in our textbook or in the ebook, if you look for the table that has indices of refraction, it's something like 1.0007, something like that. Very slightly larger than 1. And functionally, it is often okay to just swap out the speed of light in atmosphere for the speed of light in a vacuum, because the difference is very small. But if we're talking about light propagating through glass or water or maybe a gemstone, the difference between the speed of light in that material and the speed of light in a vacuum is significant, and one that really can't be overlooked or can't be ignored. So this n value gets larger when the speed of light in a material is more severely impacted. Or in other words, the larger the index of refraction, the slower light can travel through a specific material. So for example, we have a diagram here that I think this might be our first time running into this kind of generic purple wave. We're not meant to assume that the color of the light that's represented by this wave is actually purple. It's just a color that the textbook, illustrator has chosen for a generic wave. So if we were to shine, let's say, a light wave on a glass block, let's say we have vacuum on either side, but there's a section here where the light wave can actually penetrate the block and move through it and come out on the other side. We would see the wavelength changing, or we would be able to observe the wavelength changing. What we wouldn't see is a change in color. And this is something that you can kind of prove to yourself pretty simply if you have a laser pointer and like a glass of water or something like that. If you shine the laser pointer so that it is incident on the edge of your glass of water, the glass, and then it goes into the water, you're not going to see the laser turn from red to green or from green to blue or anything like that. You won't even really be able to directly evaluate the wavelength change. But since the index of refraction of glass is larger than the index of refraction of air, and the index of refraction of glass is larger than the index of water, this is why we can, this is how we can make sense of like that famous broken pencil illusion, where if you have a glass of water and you put a pencil into it, it looks like the pencil is broken at a certain area. That's just because the light that is interacting, or the light that's passing through the water, is not traveling at the same speed as it travels in the glass, nor the same speed that it travels in the atmosphere. So you won't be able to directly see the wavelength growing or shrinking when you go from one medium to the next, but you can kind of see the effect of that change in speed, because it makes the object look like it's displaced or like it is broken, when in reality it's still intact. So the frequency or the color of that light is going to remain the same, but both the speed and the wavelength change together. And if you're going from a low index material to a higher index material, the result is going to be compression, so that these wavelengths get a little bit shorter when they're going through the higher index material. And then the opposite happens when it comes out of the other side. This wavelength is going to stretch out when it goes from a large index material to a lower index material. So we've got our first thought question of the day. We have 3 different transparent materials, 1, 2, and 3. They have different indices of refraction, N1, N2, and N3. And there's a single light wave that's traveling through all 3 of them. The light wave maintains the same frequency in all 3 materials, but the speed changes at the same time that the wavelength changes. So what we're going to try to do here is determine how we can rank the indices of refraction. We don't have enough information to calculate a value for n, but we can use what we're given here in this illustration to determine how n1, 2, and 3 relate to one another. So again, take a minute to think this through and see if you can land on one of these answers, and then we'll talk it through like we did on Monday morning. Okay, so the first thing that you want to pay attention to are the interfaces, or like the boundaries between these different materials. We see that when the light ray is or the light wave is going from material 1 to material 2, it's stretching out. And if we were to roll backward a slide here, this is the same thing that we saw on the right-hand side of this example, where the wavelength gets larger when you're going from a higher index material to a lower index material. And I didn't mention it on this slide here, but anytime you see like something that's shaded like this in the illustrations from our textbook, that's meant to represent a material that has a larger index of refraction. And the thing that's unshaded is going to have the lower index of refraction. So if we go from compressed to stretched out, that's telling us that we're going from a large n to a smaller n. So this tells us that n2 has to be less than n1. So if n2 is less than n1, we can eliminate choice D because that doesn't make sense. We can eliminate choice A. And now we're down to the 2 in the middle. So let's look at the second interface. We go from a large wavelength to a smaller one. So if you go from big to small, that means that the index of refraction of the second material or the later material is going to be greater than the first one. And just to roll back again, that's what we saw on this side of the interface, where we go from a big wavelength to a smaller one. So this tells us that the index of refraction of material 3 is less than material 2. And we can use that to eliminate case C. So that even though we don't know the exact wavelengths for these 3 materials, we don't know the exact speeds, we can take just what's indicated here by looking at the interfaces or the boundaries to determine that 3's got to be the greatest, 1 is the next, and then 2 is the smallest index of refraction. Okay, so we're going to shift gears a little bit here. So before I jump into that new topic, Are there any questions or concerns about the electromagnetic wave section that we talked about? Okay, you know the rules. Jump in at any time if you do have questions about anything. What we are going to shift gears and talk about now is kind of related to the concept of the energy disturbance that we were talking about on Monday morning. So to jump backwards to the first half of our chapter notes, and this slide in particular. So when we were talking about the difference between a transverse wave and a longitudinal wave, we discussed the disturbance, or like the energy change for either the string that's up here at the top or the spring that we see at the bottom. So for the string at the top, if certain segments of string get further away from Earth's surface, we know that the gravitational potential energy is going to change for that specific segment of string. And also, if we look at certain regions on this spring, if they are either stretched out or compressed, we know that that spring is capable of storing elastic potential energy. So there's some energy component. I kind of touched on the kinematics and the dynamics. Now we can look at the relationship or the importance that energy plays in this discussion. So let's imagine that we are dealing with our longitudinal wave on a spring here. You would have to move your hand back and forth in order to make a wave propagate away from your hand. And even though it's not marked out here with dots, we can still pretty clearly see that there are certain sections of the spring that are where the coils are more closely compressed than others. So the kinetic energy that your hand is imparting to the spring is partially going to be turned into potential energy anywhere that the coils of the spring are either stretched out a little more or compressed a little bit more than they would be at equilibrium. And that entire wave pulse is moving. So that pulse itself has some kinetic energy to it as well. If you were to consistently move your hand back and forth the same distance at the same rate, what you're doing is transferring a consistent amount of energy to your medium, should be the spring in this case. And in semester one, when we encountered the concept of power, we kind of thought of it as something that we could add to our analysis of the law of conservation of energy. So just as a reminder, when we were talking about energy conservation, one of the things that made it so useful was the fact that it's not time dependent by itself, but it's also often useful to know the rate at which something is using energy or producing energy. So power in this context here is still going to be energy per unit time, but now we're going to be able to kind of link it to a wave that is propagating away from the source being your hand in this example. So if we recognize that this longitudinal wave is a good way to, or this, I should say, this longitudinal wave on a spring is a good way to model the way that a sound wave propagates through air. If we were considering some object that was making sound, we could kind of visualize these lines of constant phase, or excuse me, these planes of constant phase that we saw in our three-dimensional wave examples. So this is way back here. So think of these planes here as being exactly the same ones that we see on our power slides. So to go back to those planes are all separated by some wavelength lambda, whatever that is, determined on, or that's based on how quickly you have to be moving your hand and the properties of the spring. If we could just take a small section of that expanding shell and calculate its area, we're using a lowercase a here because we're already using capital A for the amplitude, we can introduce the concept of intensity and see how that relates to power. So again, the power is just the rate at which you deliver energy to the spring, or the rate at which maybe a loudspeaker produces sound. And if we divide this by this cross-sectional area, or this the area of this imaginary plane, the intensity should get smaller when the area gets larger. And if we remind ourselves that a three-dimensional wave, as it expands radially outward, the surface area of the imaginary shell that we're evaluating is going to get larger and larger as the radius of that shell gets larger and larger. It makes sense that let's say a loudspeaker that's producing a consistent sound with a consistent power is going to get harder and harder to hear the farther away you get from it, because the intensity is weakening, even though the loudspeaker is just continuously generating or producing energy at a consistent rate. So our intensity here is going to have power units divided by area units. And in semester 1, we encountered the watt as our power unit. That's equivalent to a joule per second. So if we divide that by an area, we have joules per second per meter squared. We're most frequently just going to leave that as watts per meter squared. So this image here on the left, imagine that this is some source of sound and that you are trying to measure the intensity or evaluate the intensity at two different distances, R1 and R2. If R2 is greater than R1, then you should expect that the intensity should be lower the further away you are from the source. But the source is just producing energy at a consistent rate. So the power of the source is going to be the commonality here. If we write an expression for the intensity at both of these locations and then combine them, because P source is the same for each one, and of course 4 pi is going to be the same for each case, we get this relationship here, where the ratio of the intensity I1 over I2 is equal to the square of R2 divided by the square of R1. Notice you've got 1 on top, or 1 in the numerator, and then 1 in the denominator on the other side, and then vice versa. That's just the result of us setting both of these expressions equal to P source and then canceling out P source and the 4 pi. So the greater R is, the smaller the intensity I2 you would experience, or you would measure. And intensity is something that is easy to conflate with loudness. Loudness is something that we can measure with a separate scale, the decibel scale. And again, here we've got a couple of, or not a couple, but another representation of the hearing span for like a healthy human ear, but it's expressed in terms of intensities inside of that rectangle. And then below, these are, I guess, loudness ratings in decibels. So we know that the lowest frequency that a healthy human ear can pick up is about 20 hertz. That, in terms of intensity, is something that we can relate to this very small value, about 1 times 10 to the negative 12 watts per square meter. So that is like the minimum intensity that a human ear can actually detect and like interpret. And then on the opposite side of that scale, there's the threshold of pain. And that's not to suggest that sounds can't be more intense than 10 watts per square meter, but this is just where it becomes physically uncomfortable to listen to that sound. So on the low end in terms of frequency, we saw that the wavelength for a 20 hertz sound wave was about 17 meters. And then on the high frequency end, or the opposite side, it was about 1.7 centimeters. In terms of loudness, if the minimum required intensity for your ear to be able to hear a sound is 10 to the negative 12 watts per square meter, then we can treat that as 0 decibel. So the lowest possible, or the lowest sound that a human ear would be capable of hearing, if that makes sense. So on the upper side of that scale, we should have a larger positive decibel rating that represents a sound that's physically painful. No negative values here. And the scale, the decibel scale, is a logarithmic one. If we know the intensity of the sound that we're evaluating, we can relate it to the intensity or the threshold intensity I naught, the 10 to the negative 12 watts per square meter, and then multiply it by 10 decibel. And we'll get a value beta. That is like the loudness of the sound that we are encountering. It's not dependent just on the intensity of that sound, but the ratio of the intensity to the threshold of hearing. And notice here, there is no, well, let me state it this way. This I is an intensity, so that's a power per surface area. There is an R, or like a distance from the sound, that's incorporated in the numerator of this expression inside the log. So that's how we can kind of incorporate the relationship between the distance between you and a sound and the loudness of that sound. I think we've got some practice problems coming up. Yeah, we do. So just to take a look at these before I switch over to the tablet, we have two questions that go together. The sound intensity 5.0 meters from a wailing siren is 0.20 watts per square meter. How loud is it in decibels? And then 5, this introduces the weakest intensity that you are likely to be able to pick out over background noise. This is different than the minimum threshold of hearing. It's related to not just your ear knowing that or being able to confirm that a sound is present, but being able to separate that sound out or to identify that sound with respect to background noise. So that's about 1.0 times 10 to the negative 6 watts per square meter. What we can do is use what we know about the siren from question 4 to figure out how far away you would have to get from that siren before you would not be able to hear it anymore. And again, that's not because the siren is not producing any sound. You just won't be able to pick it out above ordinary ambient noise. Okay, so let's swap here. Oh, and I think I need to read, there we go. Okay, so the sound intensity a known distance away from a wailing siren is 0.20 watts per square meter. How loud is it in decibels? So what we want to take into account here, or what we want to kind of recognize, is that this value here, 0.20 watts per square meter, is the intensity. We need to compare this to the minimum threshold of hearing. So that was 1 times 10 to the negative 12 watts per square meter. And we're looking for a loudness in decibels. So we're going to solve for beta. So this is the formula or the equation that we want to refer to. Beta is equal to 10 decibel times the log of I over I naught. So let's plug in what we know. We have 0.20 watts per square meter divided by 1 times 10 to the negative 12 watts per square meter. So inside of that log, the units are going to drop out. So 0.2 over 1 times 10 to the minus 12. That's going to give us 2 times 10 to the positive 11 inside those parentheses. And with no units because they cancel out. If I take the log of that value, it's going to be 10 decibel times 11.30. So that all we have to do now is multiply this. We get 113.0 decibel. And let's look at our sig figs. We have 2 sig figs from our intensity. So we're going to take this to 110 decibel. So that's how loud that siren would sound based on its intensity. So in other words, we come back up here. Remember, this is the rate at which energy is being delivered by the siren, or the rate at which the siren is producing energy per square meter. Rate of energy production per square meter. It didn't depend on knowing that you were 5 meters away from the siren. That's going to be helpful for the next question. But if you know the intensity, you could work backward to figure out what the power is. But if we're just trying to use an intensity to figure out a loudness or like a decibel rating, it's unnecessary. It's redundant information. But like I mentioned, it is going to be important in example 5, where we try to calculate how far you could get from that siren before you wouldn't be able to distinguish between it and background noise. So before I go to the next page, are we all good with example number 4? All right, let's go to number 5. So the weakest intensity likely to be heard over background noise is 1.0 times 10 to the negative 6 watts per square meter. So I'm going to call that I sub B for background. We'll say maybe BM for background noise. 1.0 times 10 to the negative 6 watts per square meter. Let's see. I have a lecture that, for the question in the chat about how quickly these will be on Canvas, I have a lecture that starts right after we wrap up here. So I won't have the time to kind of organize it immediately, but they will be up on Canvas by the end of the day. I have office hours from 1 to 3, so I should be able to get that done in that time. And I'm going to try to minimize the number of files that I upload. So I'll do like all of the chapter 16 examples together and all of the chapter 17 examples together if I can. And I'll just state that no matter what we get through today, because we're unlikely to make it all the way through the very last example today, I'll just upload the file at the end of our lecture week. So Wednesday, no matter what, I'll just put everything that we have for that week up in one file. Okay, so what we need to carry over from example number 1 is the 5.0 meter distance. The intensity that matched up with that location, I'm going to call that I1. That was 0.20 watts per square meter. So we are trying to determine R2, where R2 as a location is going to match up with the place where the background noise is. It has a specific intensity, so 1.0 times 10 to the minus 6. So in other words, I background noise and I2 are the same value. Okay, so let's just real quick make a sketch of what we're trying to evaluate here. We've got, move that over so I have enough room. We'll say this is R2. This can be R1, and then here's our source there in the center. R1 is red, R2 is green. We know I1 and I2. So we can go back to that expression that we saw in our notes, and it's not real easy for me to share. I can't share back and forth here, so I'm just going to go back to the slide and I'll read it to you just as a reminder. It's slide 15. We know that if we know I1 over I2, this is going to be equal to R2 quantity squared over R1 quantity squared. So we have everything except for R2. So R2 is going to be I1 times R1 squared over I2 square root, which makes sense because I1 and I2 have the same unit, so they'll cancel out. And I'm solving for an R. I have an R squared underneath a radical. So R2 is going to be the square root of I1. So I1 is the intensity at location R1. We were given that from the previous problem. That's 0.20 watts per square meter. R1 is the 5.0 meters. That wasn't relevant in the previous problem, but it is relevant here. And I2 is the same as the background intensity. So that is 1.0 times 10 to the negative 6 watts per square meter. That will give us R2. And let's take this step by step. R2 is going to be the square root of, this is going to be 5 in the numerator, 5 watts in the numerator. And if we divide that by 1.0 times 10 to the negative 6, we get 5 million. So 5 times 10 to the 6. I should say 5.0 times 10 to the 6. And 5.0 here. That's going to be meters squared because the only unit that survives is the meter squared that's in the denominator of our I2 value. So 5.0 times 10 to the 6 meters squared. When we take that square root, we're going to end up with 2,236.07, let's say, meters. So we have 2 sig figs to work with. Let's call that 2,200 meters or 2.2 kilometers. So not an insignificant distance at all. These are, 0.2 watts per square meter at a distance of 5 meters is actually very, very intense. We just showed that it would equate to around 113 decibels if you were standing that close to it. So that means that you could go more than 2 kilometers away and still be able to hear this sound. So here is, let's say R2 is 2.2 kilometers. Okay. So let's get back on track here. So here. Okay. out. Okay, so the last topic here is going to involve the Doppler effect. This is something that we all experience kind of maybe without paying much attention to it in everyday life. The easiest way to think of an example of it is to think through what happens to you when you are at a railroad crossing and a train that's coming towards you blows its whistle, and it sounds like the pitch of that whistle changes as you are or as the train is passing you by. Really, the only thing that's happening is that the sound wave that's being emitted by that train is going to be influenced by the fact that the train is moving. So when the train is approaching you, that sound wave is going to end up being compressed. So it's as if you could take a wave and then squish it in on itself so that the wavelength gets smaller, but the frequency that you would observe would be higher. And then the opposite happens when the source is moving away from you. So after it's passed you by, it's as if that same wave is being stretched out, so beyond its equilibrium, and it's stretched out even further so that you interpret that as a longer wavelength sound, which is a lower frequency. However, if you are inside of the train, you don't hear any difference whatsoever because you and the whistle are traveling at the same speed. So you would just observe the natural frequency, which we're going to denote with an F naught. And this link here, it takes to a flash animation. So this is outdated here. If you are curious, you can download these things. These are from the astronomy department at the University of Nebraska-Lincoln. And I use them in another class, but there are some illustrations here that are helpful for what we're talking about now. See if I can find one of them. Yeah. Okay, so let me switch. So if you were to follow that link in the notes and try to access that old Flash animation, it will take you toward a place where you can download this if you care. It's not required that you download it. But this lets us kind of visually see why the Doppler effect works, like what causes the Doppler effect. So let me move this out of the way if I can. It's like WebEx is lagging for me for a moment, so bear with me. Let's see. Can you still hear me okay? Okay. Thanks for the confirmation. Like I'm looking down at my tablet and stuff seems okay from here, but it looks like my computer's frozen, or at least what WebEx is frozen here. Well, this is not responding. I think I should be open this thing again and give it another shot. All right, this looks a little bit better. Okay, so if you are really interested in this simulation, if you follow the link that's in the notes, it won't take you directly to the Flash animation, but it will take you to a place where you can download this. If you're interested, look for Doppler shift demonstrator. What we can do is, let's see, start a mission. Okay, so I've got this source dot here that's producing a signal that has a consistent wavelength. It is expanding, or these wavefronts are expanding outward, just as we would expect to see if we were looking at the surface of a pond. And then you are the observer here. So if the source is stationary and the observer stationary, they both agree on the wavelength and the frequency of the source. But if we start moving the observer toward the source, look at what happens in the waves detected by observer section. So I'll pause this here. The wavelengths have gone from large to small. So if this were a sound wave, we would observe a change in frequency. We resume this here and look at the opposite. So when the observer is moving away from the source, now what the observer detects is a wave that has a much larger wavelength. So that means a lower frequency. So if this is a sound, the pitch would sound like it drops down. And you can also see how changing the source affects this. So one thing to pay attention to here is that when the source is actually moving, the position where the sound source is like producing a wavefront, that's going to change from time to time. So as we saw previously, the observer could move around however they wanted relative to the source, and the source would always be producing a signal that had exactly the same wavelength on the leading end and the trailing end. But now that's different. The wavelength that you would measure on the right side of the sound source is different than what you would observe on the left side. So that has the effect, if I resume here, it has the effect of causing the waves detected by the observer to have a smaller wavelength. So they're shrinking in again if we look right here. And then of course we do the opposite, we would see the opposite. Now the wavefronts are squishing together more closely on the left side than on the right. So to up here, let me stop sharing on that side. And then I'll leave you with this idea here, or this concept. We can take what we know about the speed of sound in this medium